All right, we're going to write an algorithm to find a given integer in an array that has been rotated. The array was sorted in ascending order before being rotated, and we don't know how many times it was rotated. And obviously we could do this in O of n time by just walking through each item in the array and seeing if it matches our target. But we can actually do it a little bit faster using a binary search, which would give it a log n complexity. And what we'll do is say we have our array of 6, 7, 8, 1, 2, 3, 4, 5. Then obviously it's been rotated up till this point 8, so it was rotated 3 times. And what we want to do is find that place where it is kind of a pivot point. So where it ends that rotation and we get started with the original part of the array, or the original beginning. So in this case, it would be at the 8. So in order to find that pivot point, we need to look for an element that exists where the number on the right of it is less than itself. And since we knew that it was sorted in ascending order, that's the only place where that's going to occur. Otherwise, every time you look to the right, that element will always be greater. So we can go ahead and we can also do kind of a modified binary search to find that pivot point as well. So let's go ahead and write that function first. And we'll have it return the index of the pivot point. So like find the pivot, and it takes in an array. And we're going to make it recursive, so it will also have a left and it'll have a right. Okay, so we go in and make our base cases. So if left equals right, then we know we've gone through the whole thing, they're equal, and we can return left. If left ever goes greater than right, then we know that there is no pivot, so we can return -1. And then we just get right into it and say, okay, if we got a midpoint we need, left plus right divided by 2. And then we can check to see if the place where we're at in our midpoint is the actual pivot. So we could say, okay, if if array at mid is less than the right. Oh, because we want to make sure also that we don't have a situation where, or we want to make sure, like, is the midpoint even possible to be that by making sure that it's less than our rightmost. So, because if it were greater, then we would already know we don't need that condition. So then, and then we want to see, and if array at mid is greater than array at mid plus 1, then we know that we've got our midpoint, because like we said, that second to the right element would always be greater in the case of the midpoint. So if we're looking at this 8 here, the mid is greater than its neighbor. So then we can return mid because we know we found that pivot point. If and I just realized as I was writing this, it's if mid is less than right. Okay, so if mid is greater than left and array at mid is less than array at mid minus 1, So this would be a case where, let's say we were here at like pointing at this one, and then we would say, okay, if its neighbor to the left of it is greater than, then we know that its neighbor is the mid. So it would be return mid minus 1. And then otherwise, we didn't find it yet. And so we would say, okay, well, if the leftmost item, so if we were looking here, if this 6 here is greater than or equal to the mid, so when we're looking at this 6 here, it would mean that our mid was probably here at the 3. And if it's greater than or equal to that, then we know that we want to look on the left. So if it's greater than or equal to the array at mid. So then we want to go to the left. So then we would just recursively go through and throw out that right side. So find pivot, and it takes array and left, and the right side we're getting rid of. So mid minus 1, because we know mid isn't possible. So we can go 1 less. And then otherwise, we know we want to look at the right side. So otherwise, we're going to return find pivot, array, and it's going to be mid plus 1 and right. Okay, so there's our find pivot function that we can use to find our pivot point. And then we're going to also just do kind of a standard binary search looking for our target. So we can, and it's going to return the index of it. So we've got our search, and it takes in an array of integers and a left, a right, and the target. Okay, and so we get in there, and first we have our base case. If left is greater than the right, then we know that there's nothing that we found. Okay, and then otherwise, we need a midpoint. Plus left divided by 2. And we just go through, and first we want to make sure if array at mid equals target, obviously that's our case to get out of our recursion and to and that we've got the answer, so return mid. Otherwise, we're going to look on the left side of the pivot, and then the right side. And that's the key with this search, is we're actually going to be sending in the pivot dimensions instead of the entire array. So basically, if array at mid is greater than the target, then we know that we need to go to the left. So return, search, array, left, mid minus 1, and target. And then otherwise, else we're going to go and look to the right, search array, and then we get mid plus 1, right, and target. Okay, and then that will just give us, the index of that value that we're searching for. And then we'll write a helper function to kind of pull this all together. So it can be like, and it's just going to return the index of the found item. Just call it find target. And it takes in an array of integers and the target that we're looking for. And it can do some checks first. If array.length equals 0, or if array equals null, we can just return -1 or throw an exception. And then we can say we need our pivot. So our pivot is going to equal, what did we call that? We called it find pivot. Equal find pivot, and we're sending it the array, and then the left and the right. And I think that that is all that that means. We'll just kind of end it there. And then what we can do is first check to make sure there was a pivot, because if there wasn't a pivot found, then that means the array was already, it was not rotated. So if pivot equals -1, then we can do the answer to our search, return search, and it can be just normal boundaries. So the array, and then 0 array.length -1, and then target. Otherwise, we want to split, we want to actually do our search based on where our pivot is. So if the target, so if array at the pivot, well, yeah, let's check that. So if array at our pivot equals target, then we don't even have to go into our search. So if that happens, then just return pivot. Then we have the condition of if the, we can kind of figure out which side we want to look at. So if an array at 0, the first element in the array, is less than the target, then we know that we want to look at the left side of the pivot. So we can do return search, and that's going to be our array. It's going to be left, which is 0, and then to the pivot -1, and we give it our target. Okay, and then otherwise, if none of those conditions reach, it means we want to look at the right side of the pivot. So we can just hit return, search, and we're going array, we're going pivot +1. We're going, the right side is array.length -1, and then our target. Okay, and so that would return the index of our target that we're hoping for. All right, so we can go in here and kind of do a quick walkthrough of our program to see if it works. So let's go in and make this a little bigger. Let's say we have 6, 7, 8, 1, 2, 3, 4, and 5. And let's say, let's go ahead and index these. Okay, so we're going to go in, and let's say our target is 3. All right, so target equals 3. So what we'll do is, first we go into our find target function, and it's going to pass in the array and the target, and the array does not equal 0 or is not null, so we don't worry about that. So we figure out our pivot, and so to get pivot, it's going to send an the array at 0 and the array.length. So we go into pivot up here, and we're going to keep track of, we'll make it as a stack since it's a recursive function. All right, and when it first goes in, it's got left at 0, right is 7, and this is number 1. Okay, so it goes into find pivot. Left does not equal right, so we don't worry about that. If left is greater than right, that is also not true. So mid is going to be left plus right divided by 2. So 7 divided by 2, and we truncate it, so that's going to be 3. So here's mid. And so if mid is less than right, which it is, and array at mid is greater than array at mid plus 1. So 1, if that's greater than array plus 2, that's not true. So if mid is greater than or left, which it is, and array at mid is less than array at mid minus 1, which it is, then return mid minus 1. So return this. So that means that we already found our pivot, and we get out of this recursion, and we now know that pivot equals 2. Okay, so we got through that. And then the next step is to, after we found our pivot here, we're going to go in if pivot equals -1, which it doesn't. So if array at pivot equals target, so it's 8, that does not, so that doesn't hold true. So if array at 0 is less than target, so 6, and it's not less than, so we're going to search at our, we're going to search the right half is what's going to happen. So we're here, and we're going to return that search. So let's go ahead and make a stack to follow this recursion for this function. And we're going to get length is being sent in as pivot plus 1. So 2 plus 1 is 3. I mean, left is that. And then right is going to be array at length minus 1, so 7. We go into our search, and it's if left is greater than right, which it's not. Okay, so int mid equals right plus left divided by 2. So mid is going to be 7 plus 3, which is 10 divided by 2. So mid is 5 right here. And then we go in if array of mid equals target, which actually it does, then we're just returning mid. So then we just return this 5 all the way out, and that takes us out of our program, and we're back in find target where it's just going to return that 5. Okay, and the complexity of this is going to be an O of log n because of we are dividing our number set in half each time we go through because of the binary search, and because of our pivot finding is also a modified binary search. So it's O of log n, and we are using no additional space.